Good afternoon, sir.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
So just give me 2 minutes. Okay, can you see the screen?
Yes, sir.
Yes, sir.
Okay. So almost 25 students are there. May some will join later on. Myself is Mr. Kailas Doke from Abeda Inamdar Senior College. I'm working in this college since 1998, and I'm having teaching experience around 28 years. My specialization is physical chemistry. Today, I'm going to uh, recapitulate rather than to say teaching one of the Ph.D. coursework. After your research methodology, I think research methodology course is going on. Simultaneously, from today, I'm going to start one of the course which is compulsory in the coursework, PhD coursework, which is title of the course is instrumental analysis. And one of the topics from the instrumental analysis is a X-ray analysis and electron surface analysis. Only these two subtopics are there, and this topic is given by SPPU in the syllabus for 4 hours. So, as far as possible, I will cover the contents of important concepts of X-ray methods and about the electron surface methods for analysis, which covers in brief techniques and some of the applications in the research purpose. Okay, can you hear me?
Yes, sir.
Yes, sir.
So,
Yes, sir.
this is just introduction about the X-ray techniques. And nowadays, this technique is versatile and widely used in research purpose, especially for material analysis, especially for solid material analysis, due to its a strong ability to probe the structure of materials at atomic and molecular levels. There are so many types of X-ray methods of analysis that you are aware about these methods. X-ray diffraction, in short, it is called as a XRD. X-ray fluorescence, it is another techniques. X-ray photoelectron spectroscopy, that is also very important techniques. Next one is X-ray absorption spectroscopy. Next one is a computed tomography, X-ray computed tomography, which visually we call it as a CT scan. Small angle X-ray scattering, energy dispersive X-ray spectroscopy, and X-ray microscopy. So all these are the different types of X-ray methods of analysis. And within 4 hours to cover the techniques and applications of all the four methods is impossible, highly impossible. So, with respect to research purpose, nowadays, this X-ray diffraction method is commonly used and X-ray photoelectron spectroscopic method is commonly used. So as far as concerned with this course, instrumental analysis, I am going to focus on these two techniques only. 90% of the material analysis is carried out by using X-ray diffraction or by using X-ray photoelectron spectroscopic methods. Rest of the methods is also applied, but which are little bit having different applications. In nanomaterials, nowadays, this small angle X-ray scattering method is also commonly used, and EDX or EDS, these two methods is commonly used. So in the next course of nanomaterials, which is optional course, I'm going to explain in detail about these two methods, especially small angle X-ray scattering and energy dispersive X-ray spectroscopy. So today and tomorrow, we are going to revise, discuss some applications of X-ray diffraction and X-ray photoelectron spectroscopy. Techniques you must know, basic principle you must know before to understand. Everyone knows these techniques. I think majority of the coursework students probably from organic chemistry. Some of them may be from inorganic chemistry specialization. Some of them may be from analytical. Some of them may be from biochemistry or maybe physical chemistry. These two techniques, physical chemist knows in special courses of second year physical chemistry. These two courses were taught in the PG level, X-ray diffraction. But for first year also, and in undergraduate classes also, you are familiar with these X-ray diffraction techniques. So we will begin today with the X-ray diffraction, and if time permits, we will go for introductory part of X-ray photoelectron spectroscopy. Now in the introduction, can you see the slide? Students, can
Yes,
you
sir.
Yes, sir.
Okay. So
Yes, sir.
backbone of this X-ray technique is this person who discovered X-ray. Can anyone tell me who was the discoverer of X-ray?
Ranjan.
W.C. Ranjan.
Yeah, good. So Ranjan discovered X radiation in 1895, and after the discovery and his application, he got the first ever Nobel Prize in physics, that is in 1901. So how he discovered the X-ray? What is the X-ray? Because in the X-ray techniques, the incident radiation should be X-ray. In NMR techniques or in ESR techniques or in UV, in visible, in IR, the radiations are another electromagnetic radiations. X-ray is also electromagnetic radiation. Gamma ray is also electromagnetic radiation. UV radiation is electromagnetic radiation. Microwave radiation is also electromagnetic radiation. So how he was discover X-ray? What is X-ray? That you must know as a revision part. So X-ray normally in the diagrams of X-ray methods of analysis, it was shown some tubes, small tubes, and X-ray is coming from the X-ray tube. That type of explanation or in the diagram, which is quoted in every textbooks or every reference book, every research paper. So what is the X-ray and how it is generated? The another question is that why the radiation he was called as a X-ray? Can anyone knows why he was called as a X-ray?
So can I tell?
Yes.
Sir, Ranjan don't know the exact property of X-ray. That's why he gave the name of X.
Good, good. So X-ray was unknown, its property was unknown, wavelength was unknown, characteristics was unknown. So what he thought, these peoples were physicists, chemists, mathematicians, and in mathematics normally anything is unknown, variable. Usually we call it as a X. That's why he called as a X-ray. So in the X-ray tube, this is just a block diagram of X-ray tube. And it consists of uh, two electrodes. One is cathode and one is anode. One electrode is cathode and one electrode is anode. Cathode and anodes, two oppositely charged electrodes where the electricity is applied, strong electric field is applied. And in the X-ray tubes, the electron is coming from cathode, whose energy is very high, high electricity is applied, and it is bombarded on anode. So what might be the charge on cathode and anode? Which will be positive electrode and which will be the negative electrode?
Cathode negative, anode positive.
Cathode is a negative electrode and anode is a positive electrodes. That's why electron is traveling from negative electrode to positive electrode, since electron is a negatively charged particles. So when it bombards high energy electrons bombards on the target anodes, some process takes place, and because of that process, photon is emitted, light is emitted, and that light photon, the Röntgen was called as a X-ray photon or X-ray radiation. Now, question arises how X radiation is generated on surface of anode. You can see the next slide, how X radiation is generated in the X-ray tubes. So where the cathode is negative electrode, which is having extra electron generator, that electron is incident on surface of copper metal, which acts as an anode, or magnesium metal or aluminum metals. These metals are good conductor metals. And what happens when these high energetic electrons is incident, that electron travels towards the core cell electrons and it ejects the electrons as a secondary electrons. The system, copper metal becomes unstable. To maintain the stability of the system as far as possible, the electron from valence cell jumps to core cell electrons, and there is an energy difference between K cell electron with L cell electron, 1s electron with 2p electron, or K cell electron with the L cell electron. And whatever the energy difference that electron jumps, because of that electron jumps, this L cell electron is having more energy than K cell electron. So if the L cell electron jumps to K cell electron, the energy of electron is lost, and whatever the energy difference between the L cell electron with the K cell electron, the energy is liberated in the form of photons, and that photon is called as a X-ray. That photon is called as a X-ray. Normally, this X-ray, if you read the research paper, this X-ray is called as a copper K alpha X-ray, or magnesium K alpha X-ray, or aluminum K alpha X-ray, or tungsten K alpha X-ray. So why these X-ray are called as a magnesium K alpha or copper K alpha? Since in this diagram I am showing that the copper metal is anode, so therefore the anode target material is a copper, and the core cell electron is ejected from the K cell, so therefore this symbol or this nomenclature is called as a copper K. And why it is called as alpha? In the spectroscopic notation of these two different energy level, it is to be called as a alpha, beta, gamma in the Greek letters. This L cell is called as a alpha cell also. So the electron jumps from alpha cell to or alpha electron to k electron, 2p electron to 1s electron. Therefore, these radiations are called as a copper k alpha radiation. X radiation is called as a copper k alpha radiation. Okay? Can you understand this?
Yes.
Yes, sir.
Okay, this is very fundamental, but you must know the fundamentals of why the X-ray is called as a copper K alpha X-ray or magnesium K alpha X-ray or aluminum K alpha X-ray. So these are the next slide. If you can see that these anode materials, we can use magnesium, aluminum, copper, molybdenum, tungsten, and accordingly these wavelengths of K alpha 1 or K alpha 2 or K beta 1, the energies and wavelengths are given. So what is that alpha 1 and what is that alpha 2 symbols is also mentioned over in this particular energy level diagrams. This you can find in any of the reference books or textbooks or any of the internet materials. Now, what are the basic principles of X-ray techniques? What I have mentioned in the previous two slides, different types of X-ray techniques. When X radiation coming from copper anode material, when it interacts with our system is made from atoms and molecules, then you observe different phenomenons. Maybe scattering phenomenon, maybe observed, fluorescence phenomenon may be observed, or Compton scattering phenomenon may be observed, or maybe electrons is ejected from the system, which we call it as a photoelectrons, also called as a Compton electrons, depending upon different principle, also called as an agar electrons. So, for example, in the next figure, if you can see that this is a X-ray, and if this X radiation is not collide with the systems of the material, target material, there will be no interaction, no change in the direction, no scattering will be occurs. But if the X-ray is incident on solid material or research material, and when it collides with the valence electron, the electron is ejected from the valence electron, and that electron is called as a recoil electron or Compton electron also. But to remove the electron from valence shell, it requires very less energy, and X-ray is having more energy. Even ultraviolet radiation is have that much energy to remove the electron from the valence shell, and we can observe the Compton scattering in UV spectroscopy also. So whenever X radiation scattered from the constituent electrons, the frequency or energy of scattered radiation is different than frequency of incident radiation. Definitely, some of the energy of X radiation is utilized to remove the electron from the core shell. So therefore, the scattered radiation is having less energy than the incident radiation. Such a scattering is called as a inelastic scattering. Such a scattering is called as a inelastic scattering. What is a Rayleigh scattering? The Rayleigh scattering is that when X radiation is incident on the material and when it collides with the electron, but energy is not sufficient to remove the electron. Just it changes its direction with a slight change in angle. And if the energy or frequency or wavelength of scattered radiation is identical to the energy of incident radiation, such a scattering is called as a Rayleigh scattering or elastic scattering. Every technique, this has a certain applications. Next one, when X radiation is incident and when it collides with the core shell electrons, and energy of X radiation, copper alpha, K alpha or aluminum K alpha, is sufficiently to eject the electron from core shell, such a electron is called as a photoelectron. And again, a system becomes unstable. To maintain the instability, the electron will jump from next energy cell to inner energy cell, and energy difference is removed in the form of scattered radiation, which is called as a secondary X-ray, and that is called as a X-ray fluorescence technique. That phenomenon is called as a X-ray fluorescence techniques. Each X-ray technique has a different principle, and that I'm going to explain one by one. Now, this is just an overview of all 8 X-ray techniques which are used in the research and material analysis. X-ray diffraction. First one is X-ray diffraction. That diffraction, what is X-ray diffraction? Which is a elastic scattering. X-ray diffraction is nothing but the elastic scattering. No change in energy between scattered radiation and incident radiation. So therefore, this spectroscopy, this technique is not called as a spectroscopic technique. Normally, the spectroscopy word we use whenever the system changes its energy, and the change in energy is measured by the detector. We got the change in energy recorded by the detector. We got the lines, we got the spectra. That is called as a spectroscopy. But X-ray diffraction is not the techniques which we call it as a spectroscopy. It is just an instrumental techniques. Since this X-ray diffraction is elastic scattering diffraction, no change in energy between incident X-ray and scattered radiation of X-ray. So the scattered radiation, we call it as a diffraction. That phenomenon is called as a diffraction. That's why this technique is called as a diffraction. It diffracts from the crystal surfaces, and it is useful to determine the structure of different crystals. The applications is that we can identify the phases of the solid compounds, we can study the purity of the material, and we can identify the crystal structure. This technique is non-destructive and which are very precisely used for the structural analysis. That is the advantage of X-ray diffraction techniques. Most useful techniques in the analysis of not only the crystalline solid, but for organic solids also, inorganic solids also, we can use some of the parts or some of the applications of X-ray diffraction techniques. Second, X-ray fluorescence techniques. In these techniques, the detector detects secondary X-ray emitted from the material when excited by primary X-ray. That I was told in the fluorescence, X-ray fluorescence technique. And it is also useful for composition analysis, elemental composition analysis, which we call it as a qualitative analysis for material science and in forensic science also. This is a very rapid, non-destructive techniques, and the quantity of sample required will be very, very small. Next technique is a X-ray absorption spectroscopy. Here it is called as a spectroscopy. X-ray fluorescence spectroscopy is also spectroscopy because the scattered radiation or whatever the radiation, whatever the changes takes place in the material will be either absorption of energy or emission of energy. So that's why this spectroscopy, this technique, X-ray techniques is called as a spectroscopic techniques. So it measures the absorption of X-ray as a function of energy at different ages of the elements, which are useful for chemical state identification, local structure identification, and it has a lot of advantages in the research and material analysis. Another techniques is also spectroscopic techniques, X-ray photoelectron spectroscopy techniques, which measures the kinetic energy of photoelectrons, preferably core cell electrons, either K cell or L cell electrons, 1s electron or 2p electrons or 3p electrons. That energy, kinetic energy of ejected electron is measured in this particular technique by incident X-ray. This is very useful technique in surface chemistry, identification of chemical bonding, states of the chemical compounds, especially for identification of oxidation state of the different elements, and analysis of size of thin film that can be detected by using these particular techniques. So this content of your coursework is concerned with the X-ray diffraction and X-ray photoelectron spectroscopy that I'm going to explain in details. There is another 4 more techniques which are useful. That is a computed tomography, X-ray computed tomography, XCT or CT, which measures the images, which took the images at different angles and directly creates a 3D models of the object by scanning. This is also non-destructive techniques, and we can take the images of the different composites, biological materials, fossil materials that can be taken by computed tomography. Next one is a small angle X-ray scattering. Nowadays, in the nanotechnology, the particle size is very, very small, less than 10 nanometers also. And to analyze a small surface analysis, this small angle X-ray scattering technology, which is one type of X-ray diffraction technique, subtype of X-ray diffraction techniques, which measures the scattered at different small angles. Small angle means less than 90-degree angle, and this is useful for studying the macromolecules, polymers, and nanomaterials. The next technique is EDX, energy dispersive X-ray spectroscopy. This is also commonly widely used in the various material analysis. We can analyze this technique is a X-ray technique also coupled with the SEM techniques and TEM techniques, along with the scanning electron microscopy and tunneling electron microscopy. When we couple X-ray diffraction techniques, then you will get the one new methods which is called as a EDX techniques. We can analyze the elemental analysis of metals, ceramics, polymers, semiconductors. We can identify the contaminants which are present as an impurity in the materials, and elemental mapping can be done by EDS spectroscopy. And the last one is a XRM, X-ray microscopy, which are useful to produce the high resolution 2D and 3D images of the sample, particularly useful in the biological materials, microstructure material, and micro and nanoscale material. So these are the 8 common X-ray methods of analysis. Out of that, we are going to discuss in detail X-ray diffraction and X-ray photoelectron spectroscopy. So let's begin as a revision of X-ray diffraction. Everyone is aware about this diagram. X-ray instruments, the title of this course is a instrumental analysis. So X-ray diffraction, how X-ray is generated in the X-ray tubes. So this is a source of X-ray. Parallel beam of X-ray is produced and it falls on the sample, crystal sample. And if it is a diffracted from other than 180 angle or 0 angle, then this phenomenon is called as a diffraction. And with the help of goniometer, we can measure the diffracted angles. So this is just a photograph of instrument to feel that what kind of instruments is there in the X-ray methods of analysis. Basically, this method of analysis based on Bragg's law. Everyone aware about the Bragg's law, not necessary to explain what is a Bragg's law. This is a general derivation or general mathematical equation, which we call it as the Bragg's law. N lambda is equal to 2d sine theta, where n is nothing but the order of diffraction that I'm going to explain in the next slide. Lambda is the wavelength of incident X-ray. That X-ray should be the monochromatic, so that the wavelength should be the constant. D is the distance between two diffracted planes. and this is a trigonometric mathematical function, and this is nothing but the theta, which is an angle of diffraction from the crystalline material. So this X-ray diffraction techniques is useful for analysis, particularly for crystalline material. But to differentiate between crystalline and amorphous material, when we took the XRD, we can easily say that this material will be the crystalline material and this material will be the amorphous material. That we can see after 2 slides. Now, this is a crystalline material which is having different planes, and the constituents atoms or ions are present in the one plane. This is one plane, this is second plane, third plane. So to find out the distance between these two planes, this plane has to be assigned, this plane has to be assigned what kind of plane. So when X-ray comes and it falls on constituents, atoms or electrons, when it comes to parallel beams, it is a diffracted from the surface of that crystal material or plane of the surfaces. And if it gives constructive interference, then if it gives constructive interference, then it obeys the Bragg's law. Otherwise, it does not obey the Bragg's law. Destructive interference does not obey the Bragg's law. So to get the constructive interference, this order of diffraction is very important. When we keep a path difference between first X-ray and second X-ray of one wavelength, if you keep the path difference between two X-rays is a one wavelength. This is called as a one wavelength. Wave X-ray start over here and one wave ends over here. So maxima, minima. 0 degree, maxima, again 360 degrees. So this is called as a one wavelength. If the path difference is one wavelength difference, then we call it as a order of diffraction is 1. If the path difference between two parallel beam of X-rays is 2 wavelength, then we call it as a order of diffraction is 2, and so on. So that is a significance of path difference and Bragg's law. Then and then only we got the constructive interference. So after diffraction from the sample, it is diffracted either at 45 degree angle or 35 degree angle or 25 degree angle or 90 degree angle and 135 degree angle. So from this diffracted angle theta, using the Bragg's law, we can determine the distance between these two parallel planes can be determined. And we must know the wavelength of incident X-ray, whether it is a copper K alpha 1 or copper K alpha 2 or aluminum K alpha 1 or aluminum K alpha 2. So this is just as a revision how X-ray is diffracted from the sample. The condition for X-ray diffraction, Bragg's law, that the path difference should be equal to n into lambda. And we got the derivation by the trigonometric function that path difference n lambda should be equal to 2 into d into sine theta. So that derivation that I'm not going to explain in detail. Now with the help of diffraction techniques, X-ray diffraction techniques, we can analyze two types of sample. If we got in the research single crystal, fortunately, if you got the single crystal, then we have to submit the sample in the form of single crystal in the X-ray diffraction analysis. And what interestingly we got the diffraction pattern, such a diffraction pattern. We got the different spot with the 3D models. 3D structure is observed in the single crystal diffraction. So whatever the constituents which are present on the single crystal at different spaces or different lattice within the crystal, that each constituent is diffracted at different angles, and we got the different spot. Such type of diffraction is called as a single crystal diffraction. But in the research, it is very difficult to get the pure single crystal, which size should be bigger, because to collect the crystal, the size should be bigger. And what is the powder diffraction? Not necessarily that we got the single crystal, but the sample should be in the crystalline form, although it is not in the crystal big single crystal, but it is a microscopic powder form. And what is the diffraction pattern obtained in the powder diffraction? That that powder material, small fraction of the crystals are correctly oriented in the diffraction, and we got the diffracted beams from this particular pattern. This crystal, this crystal, this crystal, they have, because they have different orientation, so different orientation of different powder, it is get diffracted at different angles. And what we observed in the diffraction pattern, we observed one-dimensional phenomenon. Only in one-dimensional, we observed number of peaks in the form of peaks, like NMR peaks, like ESR peaks. We observed different peaks at different angles. So that is the difference between first photographs we observed in the single crystal diffraction or powder diffraction, or first difference between single crystal diffraction and powder diffraction. This is another image of difference between single crystal diffraction and powder diffraction. So diffraction data in the single crystal diffraction is distributed in the 3D space. One is in the X direction, one is in the Y direction, one is in the Z direction. So 3D space spots is observed in the single crystal diffraction. That is the advantage of single crystal diffraction. But in the powder diffraction, we got that the data, diffracted data, are compressed only in one dimensional, only along this y-axis. That compressed data at different angles is observed in only one dimensional. So that is a difference, major difference between single crystal diffraction and powder diffraction. If you see in the details, the difference between single crystal diffraction and powder diffraction, what is advantage and disadvantage of single crystal diffraction and powder diffraction? For single crystal diffraction requires single and well-formed crystals. For powder diffraction, we don't need a single crystal. Powder is okay, or polycrystalline material is okay. Sample material should not be single crystal formed in the powder diffraction. The size of the crystal should be in the single crystal diffraction, should be very large enough. Either it should be minimum in the micrometer or millimeter size. It should not be in the nanometer or picometer size. It should be bigger size crystal. Bigger the size of the crystal, greater is the intensity, greater is the observation in the single crystal diffraction. But in the powder diffraction, no specific size is required. It works with the fine powder. The advantage of single crystal diffraction is that it provides 3D atomic structure from the data. It provides unit cells and symmetry directly from the diffraction patterns of the single crystal. But in the powder diffraction, it requires some calculation and average data collect using all orientation in one-dimensional patterns of the powder diffraction. Single crystal diffraction produces exact, precise information at atomic position as well as bonding, which will not be provided by powder diffraction. It will provide less detailed structure information, and taking out the average, we can predict atomic position and crystal structure. So single crystal diffraction is ideal for detailed structure studies and well-formed crystals. whereas powder diffraction is suitable for studying the polycrystalline material, mixture of polycrystalline material, or sample which is difficult to crystallize. That can be analyzed by using powder diffraction. Single crystal diffraction requires perfect crystal growths and alignments, and it is very challenging for organic chemist or inorganic chemist or physical chemist to align the single crystal or to grow the single crystal. Powder diffraction, powder formation, it is easier to perform. No single crystal is required. And since it takes some time, it is a challenging process to develop the single crystal. It is a time consuming due to crystal preparation and alignment. But powder diffraction is relatively faster. No complex sample preparation is needed. Advantage is that for single crystal diffraction, we got directly 3D data. So next step is very easy to analyze. In the powder diffraction, we have to perform lot of analysis. Experimental data is collected. We have to do calculations of that experimental data with the help of manual calculation or computers or using algorithms that converts that 1D data into 3D data. In the single crystal diffraction, the instruments which use a single crystal X-ray diffractometer, special instruments, or neutron diffractometer is also used as a single crystal diffraction. Powder X-ray diffractometer or neutron diffractometer is also used. We have not covered the neutron diffractometer. We covered here only X-ray diffractometers, the basic principle of X-ray diffractometers. So, you know something about the crystal structure, unit cell, lattices, simple lattices, body-centered lattices, face-centered lattices, Wise indices, Miller indices, lattice constant A, lattice constant B, lattice constant C, the angle along one face, along second face, along third phase, which we call it as a ABC, capital ABC, alpha, beta, gamma. And you are familiar even with the Miller indices also. So this is a one plane drawn, imaginary plane, and which is having Miller indices 100. So why it is called as a 100? Just that I'm going to explain in short, but not in details, because everyone is aware about this plane. Wise indices, Miller indices, conversion of Wise indices to Miller indices, unit cells, lattices. Now, after explaining these fundamentals, we will start to discuss some of the applications of X-ray diffraction techniques. Few of the applications, if you see the research paper, and if you find that the first application is a phase identification, particularly for this is for powder diffraction. We are concerned with the powder diffraction, not single crystal X-ray diffraction. Whatever the application is concerned only for powder diffraction, not for the single crystal diffraction, because single crystal diffraction with the help of algorithm or computed methods, we can directly get the data. We got the A, B, C values, alpha, beta, gamma values by computed technology. But in the powder diffraction, to identify the difference between whether the substance is crystalline or whether the substance is amorphous. So this is one of the spectra. Don't say spectra, it is a diffraction pattern. On y-axis, it is a intensity, and on x-axis, it is a 2 theta. That diffraction angle of instrument is measured, diffractometer is measured, and that angle is plotted against the intensity of that diffraction in one dimensional. And you can see that in case of amorphous substances, if you record the powder XRD for amorphous substances, you observe that broad hump. This is a broad hump. no any sharp peak, diffracted peaks is observed in the amorphous substances. But if our sample is a crystalline material, you can observe such type of spectra, diffracted spectra. We observed sharp diffracted peaks. This is a sharp peak with a different intensity, sharp peak with a different intensity. So to identify whether our solid compound is crystalline or amorphous, which can be easily identified, just take the XRD, powder XRD, see the spectra, see the diffracted pattern, not spectra, and you can differentiate amorphous, whether your sample is not in the crystalline form, or whether it is in the crystalline form, or whether it is in the amorphous form. Sometimes you prepare in the synthesis, material synthesis, you crystallize some material from amorphous substances, and most of the times you observe that such type of XRD powder diffraction spectra is observed, which indicates that your product is not 100% crystalline. It is a mixture of amorphous, some of the material hump is there, and some intense peak is also there. So your sample is a mixture of crystalline substances and amorphous substances. You can see the second slide. All these photographs is taken from some of the research papers, and you can see that you can clearly visible that this sample material is from amorphous material, and this sample material is from the crystalline material. So if it is a broad hump or no sharp peak, then definitely that material is a amorphous material. If it is a crystalline material, you can observe the sharp diffraction peaks. Sometimes you observe that if your material is although crystalline material, but you will observe such type of some peaks in the crystalline material. This is not because of amorphous nature. This is because of you might be aware about the signal to noise ratio of the instrument. If the signal to noise ratio of the instruments is less than 2 or less than 3, then you observe such type of noise in the diffracted peaks. So which is just noise and which is not the amorphous material. If your material is crystalline, and if you are taking XRD with the good XRD instruments, sophisticated, good quality XRD instruments, then that instruments maintain the signal to noise ratio is greater than 2 to 3. If the signal to noise ratio of instrument is greater than 2 to 3, you will definitely get the crystalline material with the sharp diffraction peak. Okay? Any doubts about the difference between crystalline and amorphous substance, students?
No, sir.
No, sir.
No, sir.
So this is one of the applications to differentiate our solid material, our product, synthesized product, whether it is a crystalline or whether it is amorphous. We can get the diffraction pattern, powder XRD, and you can easily analyze that whether it is a crystalline or whether it is a amorphous. Switching to second important application, that identification of crystal structure, which is from the powder diffraction pattern. This is just a revision slides. Everyone is aware about the 7 crystal system and 14 Bravis lattices or space lattices. So, everyone knows 7 crystal system that you might be studied in the undergraduate classes and postgraduate classes.
Yes, sir.
Cubical, tetragonal, orthorhombic, hexagonal, triclinic, monoclinic, rhombohedral. Only 7 crystal system. Why not 8 crystal system? Can anyone answer? 9 crystal system. Why only 7 crystal system? Okay. You can find the answer in the next time. Tomorrow I will ask. Or since all these are the combinations, A is equal to B is equal to C. What are these? These are the lattice constant from this to this distance along x direction, along y direction, along z direction. If they are identical, or these angles at one interface, second interface, third interface of that particular crystal, if they are identical, then it is called as a cubical crystal. These are 7 possible crystal system as per mathematics. As per mathematics, no 8th possibility or combination is available in the mathematics. Any science, physical science, physics, chemistry, any science depends upon mathematical concepts. So these are 7 crystal system, and if you see the papers, every research paper, it has been found that there is only either monoclinic crystal system or triclinic or tetragonal crystal systems. What are the Bravais lattices or space lattices? There are only 14 space lattices and Bravais lattices. So if it is a simple cubic, what is the arrangements of constituents, atoms or ions or molecules which are present in one unit cell? This is called as a smallest repeated unit of the crystal, which we call it as a unit cell. And in one unit cell, in the repeated one unit cell, what is the constituents, atoms, ions and ion, 3-dimensionally they are arranged. If they are arranged only at the corner of the cube, then it is called as a primitive cubic lattice or simple cubic lattice. Everyone aware. Along with the corner, each face, the constituent atom is present, not wholly, partially. Then such type of lattice, Bravais lattice or space lattice, to honor the Bravais, the lattice is called as a Bravais lattice, face-centered cubic. Likewise that, the cubic is also third one type, which is called as a body-centered. Along with the corner, the center of the unit cell, one whole constituent atom or ion is present of that particular
BCC.
solid material, then it is called as a body-centered cubic lattice. So one crystal system, cubic, has 3 different space lattices. Within the 3D space, in one unit cell, how the constituents, atoms are arranged, that is called as a space lattices. So likewise that, tetragonal system has only 2 lattices, hexagonal system has only 1 lattices, orthogonal 7 crystal system, it has a 4 space lattices, and rhombohedral 1, monoclinic 2 and triclinic 1. So total together, which is called as a 14 space lattices or Bravais lattices. So if we have a powder sample and if you got the XRD, and XRD shows that it is having number of sharp peak, definitely it is a crystalline material. So we have to identify what kind of crystal system it is, whether it is a tetragonal, simple cubic or face-centered cubic, whether it is a body-centered tetragonal or monoclinic or triclinic, what type of lattice is there, what is the length of A, length of B, length of C, what are the angle alpha, beta, gamma. So this can be analyzed from the diffracted peaks using some mathematical calculation. Using Bragg's law, we can analyze that particular diffracted pattern, powder diffracted patterns. Especially those crystal system out of 7 crystal system which are more symmetric, Mathematically, we can analyze that crystal structure manually using some mathematics. And those crystal system out of 7 crystal system which are asymmetric, they cannot be analyzed easily using simple mathematical knowledge. So for that we use softwares with the help of software, we can analyze each peak's diffraction pattern, what kind of that crystal system or space lattice or Bravis lattices. So out of 7 crystal system, my question is that which one is the most symmetric crystal system? Can anyone answer?
Cubic, simple cubic.
Cubic only. Simple cubic.
Is only cubic
Simple
crystal system. So how you analyze this is a symmetric, most symmetric, because here A is identical to B is identical to C, so it is a proper cube, and all the 3 angles are rectangle, 90-degree angle. So this is the most symmetric crystal. And the least symmetric crystal system is a triclinic system, where A is not identical to B, which is not identical to C. Alpha angle is not identical to beta, which is not identical to gamma, and unfortunately, which is not rectangle, 90-degree. So this is a least symmetric system, asymmetric system. So such type of asymmetric system, we need more sophisticated software to analyze the diffraction pattern. For symmetric structure, cubical structure, we can analyze using some basic knowledge, using Bragg's law and some mathematical knowledge. Easily we can analyze. We can analyze using some extra mathematical knowledge, tetragonal also, orthorhombic crystal system also, hexagonal crystal system also. Just 1 minute, hold on. So almost 1 hour is over. I am going to continue. Is it okay?
Yes, sir.
Yes, sir.
Yes, sir.
Now this is how to analyze diffraction pattern. This is silicon carbide cubical crystal, and you can see that. Can you see the photographs and visualization in the photograph? The crystal is rotating, cubical crystal is rotating, and after each rotation, the constituents angles and each planes are different. If the constituents angles and each plane has a different number of constituents atoms, accordingly, the diffraction pattern is observed. The most intense peak indicates that, if you see that, wait some time. This one is the most intense peak, where all the constituents atoms in one plane, 5 different constituents atoms. In second plane, 5 different constituents atoms. Third plane, 5 different constituents atoms. But the number of atoms is more, number of constituent atoms, ions or particle is more, population is more, the intensity is more. That is a rule of spectroscopy that is knowing to everyone. Okay? So some peaks are more intense in the diffraction pattern. Some peaks are less intense. Some peaks is having intensity around 10%. Some peak is having intensity around 80%. Some peak is having intensity around just 2 to 5%. It depends upon when the crystal, crystal at different planes has a different constituents, and therefore the number of constituents reflects in the intensity of that particular diffracted patterns. So this is a X-ray diffraction pattern for powder diffraction pattern of cubic silicon carbide, and here I have mentioned, like in the research paper, copper K alpha, which indicates that this is an anode material, copper is an anode material, and the electron is ejected from K cell, core cell. Electron jumps from L cell to K cell. Therefore, energy difference between K cell electron and L cell electron emits the radiation having different energy. The radiation is emitted in the form of X radiation having wavelength lambda 1.5418 Armstrong unit. So every research paper, this line is given. Copper K alpha line or magnesium K alpha line is given, which means that this is a source of X-ray. This is a source of X-ray, which are useful for analyzing the diffraction pattern. Now, to analyze, to identify the crystal structure, there are various steps, various mathematical calculation you have to do. And many of the students you might have in your PG or UG have analyzed such type of diffraction pattern. Just a revision, I'm going to explain one detail. I will give two exercise. You tell me what type of lattice in the Saturday, or you can submit the assignments. Okay, so first step for analyzing crystal structure or identifying crystal structure, whether it is a simple cubic or body-centered cubic or tetragonal or hexagonal, is indexing. What is meant by indexing? Normally, you are familiar with the Miller indices, which is called as a indexing. It is a indexing in terms of 1, 2, 3, 4, 0, such type of indices we use, which is called as the indexing phenomenon. So each peak has to be indexed to determine the unit cell dimensions as a B, C, angle alpha, beta, gamma. And from the peak position, we can index. The diffraction pattern can be analyzed, and it is always first step. So I told you earlier that symmetric structure can be easily analyzed using some mathematical calculation, but asymmetric structures cannot be analyzed like orthorhombic crystal or monoclinic or triclinic. Usually, we follow the methods of auto-indexing using softwares which is called as a computer algorithms that is available, and we can analyze asymmetric crystal structure with the help of auto-indexing. But we can perform indexing for the symmetric crystal structure like cubical structure. Now to index cubical structure, which is a most symmetric crystal system, you are familiar with the Bragg's law that n lambda is equal to 2d sine theta, where the order of diffraction is 1. So the equation becomes a lambda is equal to 2d sine theta. Here, HKL, these are the indices, which we call it as a Miller indices. H stands along x-axis, K stands along y-axis, L small l stand along z-axis. These are the indices along the planes. Indices along that particular planes. So HKL is introduced, and the distance between two HKL plane that can be identified by using the each diffraction pattern from the angle of diffraction. So angle of diffraction, we got the diffraction pattern. Lambda is the wavelength of incident X-ray. If it is a copper K alpha, it will be 1.54 Armstrong unit. So rearranging this equation, taking a reciprocal of 1 by d, we got another equation, rearranging this equation, further rearranging this equation for Miller indices, further rearranging this equation, we got some pattern related to sine square theta upon h square plus k square plus l square, which is equal to lambda square upon 4a square. Another equation we got 1 by d square is equal to h square plus k square plus l square divided by a square. And with the help of this equation, we can easily find out a values. That is a modification. With the help of this equation, we can find out the distance between two HKL planes in the crystal system from the diffraction peaks. So how we analyze a cubical pattern, that I'm going to explain in the next slide. This is one of the research paper. Wiley is one of the journal, published journal. It is a journal of material, and they synthesize this. Someone is speaker is on. Okay. So they synthesize strontium titanate crystal by using microwave assisted hydrothermal methods, and they got the powder form strontium titanate, and they got the spectra, powder XRD spectra. Not the spectra, it is a diffraction pattern. They observed the diffraction pattern and they analyze each peak and they index first peak as a 100, second peak as a 100, 110, third one is 111, 200, 210, 211, 220. Such type of indices is there. So this 111 stands HKL, 200 stands HKL, but different distance between two different planes. So how they index these each peaks by using some mathematical calculation, they might be used or they may be used auto-indexing. So suppose if you analyze any powder XRD, and if you don't get this diffraction pattern with the auto index, then you have to do lot of calculations. Usually, if you do XRD, powder XRD, and using any of the laboratory, research laboratory, and they took only 300 or 500 rupees the cost, they will give only diffracted patterns only. They will not analyze what kind of lattices is there, what kind of planes are there, what is the meaning of each peaks. They will not analyze. But if you analyze such type of powder material in the sophisticated instrument which cost complete analysis for 5,000 rupees for one sample, they will give you a diffraction pattern with the auto indexing. So if it is already auto indexing, this type of mathematical calculation is not required, but you have to do some another calculation to find out the volume of unit cell, what type of lattices is there, what is the unit cell length, that you have to, suppose you have to analyze. So depending upon what kind of diffraction pattern is observed in the spectrum. So this is a XRD of strontium titanate. Instead of 100 or 111 planes, I have quoted 2 theta values, because on x-axis it is a 2 theta values. X-axis, this value is a 2 theta values. So with the help of scale, we can convert that particular powder XRD in the form of 2 theta values. So this is 22.72 diffraction pattern at angle 2 theta. This is second, third, fourth, fifth, sixth, seventh, 8th, 9th, 10th, and so on. So approximately in the XRD's diffraction pattern, these are the 2 theta values. So for indexing of this diffraction pattern, we can index, we convert that indexing into one table. From 2 theta values, we can find out the theta. From theta values, we can find out the sine theta, make a square of that sine theta, square of the theta, sine theta will be fractional number, square of that fractional number is further smaller number. So to convert that smaller number into bigger number, multiplied by some bigger number, integer number, Either you have to multiply it by 10 number or 100 number or 1000 number or 10,000 number. That is your choice. So we got somewhat little bit bigger number from smaller number. Then that bigger number has to be divided by common factor. So how to find out common factor, that I will explain. And from that we can get, from the values, we can get the HKL planes and another properties. So from 2 theta, this is calculated, theta values. From 2 theta, we can find the theta by dividing 2. So these are the theta values. Taking sine square of this theta, trigonometric function, and multiplying by 1000. Sine square theta will be smaller number. By multiplying by 1000, it gives a bigger number. So this is a bigger number, 38.8, 77.93, 116.64, 156.46. So we got the bigger number. That bigger number has to be converted again into smallest integer number, smallest integral number, like 1, 2, 3, 4. So for that, we have to divide that bigger number by some common factor. So how to find out the common factor? Subtract 1000 sine square theta of first peak from second peak, or third peak minus second peak, or fourth peak minus third peak. We got a common factor. Or simply we can select first number as a common factor. First number as a common factor. In this case, I have selected first number as a common factor because 77.93 minus 38.80 is almost identical to 38.8. 116.64 minus 77.93 is again close to 38.80. Fourth value minus third value is again coming to close to first value. So I selected common factor as a second peak 1000 sine square theta minus first peak 1000 sine square theta as a common factor, which is very close to first 1000 sine square theta, which is called as a common factor. So after finding theta values of each peak, taking a sine of that theta, square of that sine of theta, and multiplying by bigger number, integer number, dividing that integer number as a first number, same number, or second number minus first number, third number minus second number, or even sometimes third number minus second number also can be used as a common factor. So what the answer we got? 38.80 by 38.80, we got complete integer number. 77.93 divided by common factor, we got almost close to second integer number. Third value divided by common factor, we got almost close to integer number. Fourth, almost close to integer number, almost close to integer number. Every number are very, very close to integer number. If not, you can round it up to. That's why this diffraction method is called as an average method, because it involves lot of calculation and average out. So this 1000 sine square theta divided by common factor is nothing but the values close to 4 sine square theta divided by a square. And one of the mathematics I showed in previous slide, which is close to h square plus k square plus l square. What are these values? S square plus k square plus l values. These are the indices along x-axis, y-axis, and z-axis. These are the unit indices, maybe 0, integer number, including 0 number, not the infinity number. because we convert that wise indices infinity number into Miller indices. So these are the pre-calculation of Miller indices. So this 1 is approximated as a 1. It is equal to 1. 2.00 is approximated as a 2. 3.006 is approximated as a 3. So likewise, we got the values of h square plus k square plus l square is nothing but the 1, 2, 3, 4, 5, 6, not 7. Interesting. 8, 9, 10, 11, 12. Maybe 13, 14, if the next peaks are there. So the value of h square plus k square plus l square is 1. So what will be the value of HKL?
100.
100. Very good. So we convert this h square plus k square plus l square into Miller indices in the indexing, and we got 100, 110, 111, only one possibility, 200, only one possibility in mathematics for 4, 2 square plus 0 square plus 0 square is a 4, 5 in integer number has a only one possibility, 210 as a Miller indices. So 2 square is a 4, 1 square is a 1, 0 square is a 0. The total of h square plus k square plus l square will be 5. Similarly for 6, only one possibility of indices, 211. Similarly for 8, 220. Here for 9 number, there are 2 possibilities of Miller indices, 221 and 300. 2 square is a 4, 2 square is a 4, 1 square is a 1, so total is 9. And 3 square, 9 plus 0 plus 0, that will be also 9. So this this peak can be indice as a 221 or 300. Both have the same meaning. Then for the next, 10 has a only one possibility, 310. 11 has a only one possibility, 311. 12 has a only one possibility, 220. So this much calculation you have to do if you got the XRD pattern without indices, and if it is a cubic, of course. If it is a non-cubic, then the mathematical calculations will be different. So after getting this pattern 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, whether what type of lattice is there in the cubical system, whether it is a simple, whether it is a body centered, or whether it is a face centered. So in the literature, this sequence is given for identifying cubical Bravis lattice or space lattice, where the value of h square plus k square plus l square, the sequence values comes as a 1, 2, 3, 4, 5, 6, 8, no 7 over here, 8, 9, 10, 11, 12, 13, 14, no 15 over here, 16, 17, 18, such type of indices is observed. If it is a body-centered cubic, then all even number, 2, 4, 6, 8, 10, 12, 14, 16, all even number. If it is a face-centered cubic lattice, it start with the 3, 4, 8, no 5, 6, 7, 8, 9, 10 is not there, 11, 12, 13, 14, 15 is not there, 16, 17, 18 is not there. Then such type of system is a face-centered cube system. And diamond cube is somewhat different. Diamond cube is somewhat different, which has indices sequence for h square, k square, l square addition is 3, 8, 11, 16, 19, 20, 24, 27, and 32. So what we analyze in the strontium titanate, the observed sequence of S square, K square, L square value comes as a 1, 2, 3, 4, 5, 6, 7 is absent, 8, 9, 10, 11, 12. This pattern, sequence pattern, is only for primitive cubic or simple cubic lattice. So strontium titanate has a cubical structure with the simple cubic lattice that we can conclude. And these planes, these Miller indices you can index in the structure like this one before publishing a paper as a 100 peak, 110 peaks, 111 peaks, 200 peaks, 210 peaks sequentially. So this calculation you have to done for each peaks, and this calculation gives only what are the indices of each peaks, Miller indices of the each peaks that you can calculate with the help of using modified Bragg's law and modified planar equation. Is it okay?
Yes, sir. Yes, sir.
Okay. Now, after getting this type of lattice, it is a simple cubic lattice or primitive cubic lattice. We can find out before publishing if it is a cubic, then A should be equal to B should be equal to C. Means we should find out either the value of A, which or B or C, which we call it as a lattice constant. After getting the lattice constant, we can find out the volume of one unit cell of this cubic lattice. And by using again mathematics, basic mathematics, that volume of cubic lattice is A raised to cube. Once you got the A, take a cube of A, we will get the volume of one unit cell in the cubic lattice. So such type of calculations you can do by further analysis of that Miller indices. Okay, how? You are familiar with this such type of planes. We can determine the interplanar distance and lattice constant. So what is the interplanar distance? That I am going to explain with the help of this slide. You are familiar with 100 plane. This is one plane and this is another plane. Plane behind and plane towards us. This is the origin of crystal. I call this as a x-axis, this as a y-axis, and this as a z-axis. By Cartesian coordinate, any axis is called as a x-axis, any axis is called as a y-axis, any axis is called as a z-axis. It is not fixed. This is as a x-axis, this is as a y-axis, this is as a z-axis. Now this plane is called as a 100 plane. How it is called as a 100 plane? Suppose this is the origin of the crystal, what we assume to explain the plane, and this is one plane, and that plane intersects along x-axis at one unit distance. This particular plane does not intersect on y-axis. The plane does not intersect on z-axis. So therefore, such a plane is called as a 100 plane. The plane intersects on x-axis at unit distance. That is the meaning of 1. Plane is parallel to y-axis and parallel to z-axis. Parallel means in the y indices may at unit distance, infinite distance, it will intersect. So in the Miller indices, that infinity inconvenient number is converted into 00 number. So this is one. This plane is called as a 100 plane. This is also 100 plane of behind this crystal. There is a one more crystal which has a origin, and this plane, backside plane, is also 100 plane. So what is the distance between these two 100 plane? That we can analyze from the diffraction pattern. This is similar to this plane. Just rotate the crystal. Axis will change, which is called as a 0, 1, 0 plane. Again, rotate the crystal. Axis will plane in the third direction. The plane is called as a 0, 0, 1 plane. So what is the distance between these two 0, 0, 1 plane, or these two 0, 1, 0 plane, or these two 1, 0, 0 plane? That distance is called as a interplanar distance. So that we can determine from the indices what we got from the diffracted peaks. And I told you that lattice constant also. Similarly, for 1, 1, 0 plane, the distance between 2, 1, 0, 0 plane, distance between 2, 1, 1, 1 plane. Although this is one unit cell, there is one more unit cell behind, one more unit cell towards us. So if you make an axis of behind unit cell, then there is one more another plane with the distance between 2, 1, 1, 0 plane or 2, 1, 1, 1 plane. This is either we call it as a 2, 0, 0 plane or 0, 0, 2, 2 plane. In this plane, there is a constituent atom. In this plane, there is a constituent atom, but we make a half of that. There is a no constituent atom. So whatever this distance between this plane is called as a 2, 0, 0 plane. Taking a Weiss indices converted into Miller indices, we got the 2, 0, 0 plane. So what this plane is called as a distance between 2, 0, 0 plane or distance between 0, 0, 2 planes, depending upon the choice of axis by rotating the axis. So these distances we can determine from the indices peak. How to determine? So we will continue the same calculation. We got the Miller indices, HKL, and we want to determine DHKL for the same plane. Use the Bragg's law. N lambda is equal to 2d sine theta. Rearrange the Bragg's equation. D is equal to n lambda by 2 sine theta. So after rearranging, putting the values, order of diffraction is 1. Wavelength of incident X-ray is copper K alpha, which was mentioned by research paper 1.54, 1 Armstrong unit. And theta is over here. Taking a sine theta, we got D100, distance between two 100 plane. The answer is 3.909 in Armstrong unit, because I put the value of lambda in Armstrong unit. So what is this distance? The distance between two 100 plane. Distance between two 100 plane. Similarly, we can calculate distance between two 110 plane by putting in the Bragg's equation, rearrange Bragg equation, where theta is a different, n is the same, lambda is the same. Since theta is a different, sine theta will be different, 2 sine theta will be different, and n lambda upon 2 sine theta will be different. So D, distance between two 110 plane, is a less than distance between 110 plane. Okay. Similarly, for 111 plane, 200 plane, you can see interestingly the distance between 200 plane is 1.947 Armstrong unit, which is almost half of 3.909 Armstrong unit. Why? The reason behind that, this is 002 plane or 200 plane. If this distance is 3.909 Armstrong unit, half of this will be definitely 3.909 divided by 2. And the answer should come as a half of that, which is 1.947 Armstrong unit. So similarly, we can calculate the distance between two planes of all Miller indices. So each peak, diffracted peaks, diffracted between two 100 plane, diffraction between two 110 plane, diffraction between two 111 plane that we observed. So after getting these d values, we can calculate the lattice constant with the rearranged Bragg's equation using 1 by d square is equal to lambda square upon and h square plus k square plus l square values, and taking square root of that, rearranging the equation, we can find out the lattice constant for all cubical crystal, whether it is a simple body centered or face centered cubic lattice. So here we find the DHKL in the previous column. H square plus k square plus l square is already over here. So just do the multiplication. Taking a square root of that h square plus k square plus l square multiplied by DHKL, we got the lattice constant for all planes in the cubical crystal. And we got the answer 3.909, 3.858, 3.904, 3.894, 3.904, 3.897, and so on. And all these numbers are almost constant. Small error is there within the limit of less than 0.1% because of taking randomly 2 theta value as average values. So if there is an error in the taking 2 theta values, that error comes in the A values also. But all these values are very close to A values. All A lattice constant for all peaks, diffracted peaks, gives the same, almost same lattice constant. And when we took the average of that, we got the answer 3.901, close to 3.90 Armstrong unit. So we got the lattice constant A, which is equal to B, which is equal to C. And we got the cubical crystal. Does it is necessary to determine alpha, beta, gamma for this symmetric crystal? Because, can you hear me?
Yes, sir.
Yes, sir.
Because in the cubical crystal, alpha, beta, gamma, they are identical and they are always
90
rectangular, 90 degree. So not necessary to determine the alpha, beta, gamma values. So this average lattice constant we calculated from the diffraction pattern of research paper. And if you go the result of that research paper, result and discussion of that research paper, you will find that the A values, lattice constant value is 3.90 Armstrong unit, which means that whatever the calculation we did in the manual indexing, determining the indices of each peak, diffracted peaks, determining the distance between two planes of diffracted peaks, and determining the lattice constant, they are correct, and average lattice constant is also correct. Is that clear?
Yes, sir.
Yes, sir.
Okay, so such type of analysis we can do manually in our calculations of our diffracted peaks. If it is not already indexed. If it is already indexed, we can do the calculation from this slide only. We can determine the D values, distance between two diffracted planes, or we can determine the lattice constant for that particular crystal system. And from the previous calculation, we got from this sequence of h square plus k square plus l square for cubical crystal is a simple cubic lattice. So we got lot of information of the sample strontium titanate, which we are analyzed in that research paper of nanoparticles. Okay. Now, this is another research paper, nanoscale research letter, which is a Springer journal, and I'm directly taken second figures of X-ray analysis. This is the nanomaterial, solid material obtained by gold nanoparticles, biosynthesized gold nanoparticle, and it gives some almost intense peaks. One is at 38.1 2 theta value, second is 44.3, third is 64.5 2 theta value, fifth is a 77.7. And they were indexed also in the research paper as a 111, 200, 220, 311. So after indexing, not necessary to do the calculation, you can do the calculation and whether confirm that the research paper publish, whether that lattice is a simple body centered or face centered, you can confirm by doing all these calculation. But we have literature data and sequence values is given over in the diffracted peak as a 111, 200, 220 and 311. So from this gold nanoparticle diffracted peak and indices, we can say that what type of cubic lattice is either simple, primitive, body-centered, face-centered, or diamond cubic lattice. So if this 111 Miller indices indicates that the value of h square plus k square plus l square will be equal to 3. The value of 2 square plus 0 square plus 0 square will be 4. The value of 220, the 2 square plus 2 square plus 0 square will be 8. The value of 3 square plus 1 square plus 1 square will be
11.
So only 4 peaks are there. And their sequence value is a 3, 4, 8, 11, which is not in the cubical lattice, which is not there in the body-centered cubic lattice, but in the face-centered cubic lattice, you can observe that the first four peak. So we have to start with the first peak compulsory for analyzing any crystal. Although it is a small peak, but it should be analyzed. Then and then only the indexing pattern will be correct. So 3, 4, 8. Next peak is not mentioned or shown in this particular XRD analysis of gold nanoparticle. It might be next peak is there, next peak is there. So this sequence 3, 4, 8, 11 definitely indicates that.
Excuse me, sir. Hello, sir. Hello.
Yes.
Sir, are you presenting the XRD spectrum of that gold nanoparticles? Because we are not able to see that presentation on the screen.
Okay. I'm presenting. That's why communication is not there. Just wait.
It is visible, sir.
Okay. Some students are not.
Sir.
Yes,
sir. Now it is visible.
Okay. So
yes, sir, now it is visible.
Okay. So the pattern, sequencing pattern started with 3, 4, 8, 11. No, 5, 6, 7, 9, 10 is not there. 11, next maybe 12, next peak maybe 13. So definitely this gold nanoparticle, synthesized gold nanoparticle is from the face-centered cubic lattice. 100% FCC lattice. What is a FCC lattice that I have shown over here? Actual crystal structure of FCC lattice with the proper spacing. Corner, 8 constituent corner, partially 1 unit cell consists of some constituent atom, partially, and each space, there are 6 spaces, 3 can be visible in this direction, 3 is behind, face centered. So this type of lattice is a gold nanoparticle. Is that clear?
Yes, sir.
Okay, so we can determine D11 plane, distance between two D11 plane or D200 plane or D220 plane. We can determine the unit volume, lattice constant. That parameters you can determine easily by for symmetric crystal, like a simple cubic crystal. We can do calculation for hexagonal also, tetragonal also, because they are also somewhat symmetrical. But the calculation is very tedious, which requires lot of extra mathematical knowledge. A lot of calculation is there, and then after doing lot of calculation of 2 hours calculation, finally we got whether the crystal system is tetragonal or hexagonal. But for simple symmetrical cubical lattice, we can manually indices cubical crystal, and we can determine all the parameters which is present in the required in the research paper. This is another paper, Springer Link, Journal of Cluster Science, which was published in August 2021. They synthesize and they characterize magnesium oxide nanoparticles. They determine crystal size and strain of magnesium oxide nanoparticles by using Williamson-Hall method. And they got some answers, so that we can also analyze. We can determine the crystalline size. We can determine another parameters with the help of our basic chemistry knowledge, basic physics knowledge, or basic mathematical knowledge. How? You can see that they synthesize 2 magnesium oxide nanoparticles using 2 different NaOH concentration, because NaOH is used in the hydroxide, any oxide crystal nanoparticles. So 2 different NaOH concentration, and they call it as a MgO1 and MgO2 nanoparticles. And if you see that, the pattern indicates that it is 100% crystalline, no hump. So 100% pure crystal, pure crystalline substances, and they index each peaks with the values 111, 200, 220, 311, 222 by mathematical calculation. So again, you will observe that for both the magnesium oxide crystal, the indexing pattern of H square plus K square plus L square will come as a 3, 4, 8, then next is a 9, next is a 12. Such type of pattern is observed, which indicates that there is a missing 1 peaks. Yeah, 11, not 9, 11, 12, which indicates that again this magnesium oxide nanoparticle is a FCC types of lattice. Is that clear?
Yes, sir.
Okay. Further, they analyze what is the size, average size, because it is not single XRD, single crystal XRD. Single crystal XRD gives the exact size, but in the powder XRD, we got the average size. So we can use mathematical equation, physics equation to determine the average crystallite size of these nanoparticles. How they use? They use this particular mathematical equation. Every research paper, the crystallized size of nanoparticles or crystalline material is obtained by this Debye-Schreier equation, and they got the Nobel Prize also for this particular equation. So directly the D values, crystallite size of any crystalline material is obtained by formulae using K into lambda divided by beta D into cos theta. So it is not concerned with the sine theta, it is concerned with the cos theta. Where, what is the K value? K value is the characteristics of that substance, the shape of the constant, and for cubical crystal, because we got the cubical system, so for cubical crystal, the value is close to 0.9. K is a constant for cubical crystal. Every crystal has a K values, and which is a different. So for a cubical crystal, whether it is a simple body centered or face centered, the value is close to 0.91 exact value. Lambda is the wavelength of incident radiation, which is copper K alpha radiation. Beta D is nothing but the full width of diffraction by peak at half maximum intensity. That we have to determine by using mathematical calculation. And theta is nothing but the diffraction angle, which is obtained from sine theta, or which is obtained from 2 theta. So we can determine D values of this 2 magnesium oxide crystal using only 2 intense peak. They calculated for another peaks also, but because of shortage of time, I will show only for 200 plane, which is intense peak. Why intense peak we consider? Because in the previous calculation, I showed that the A value we got accurately with the help of all intense peak, or intense peak, which is the most intense peak present in the diffraction pattern in the crystal structure. So beta D values is nothing but the full width at half maxima that is obtained from most intense peak. So we should have a soft copy of this XRD, and we should have origin software with us. And with the help of origin software, that soft copy of this particular intense peak can be enlarged into one big peak. This is a maximum intensity of peak, and with the help of this maximum intensity of peak, using some mathematical calculation, half intensity values. What is the width of the peak? This is called as a full width of the peak. This is a half intensity peak, where what is the width? This W value. This W value is called as a beta D. And this beta D can be easily obtained from origin software, which is available, freely available, or which can be available in the paid for few months or few years. We can take that origin software. So from the intense peak, we can determine full width for this calculation. For every peaks, we can determine FWHM. But here I'm showing only for intense peak. So what is the calculation I have shown using this Debye-Schreiber equation only for 200 intense peak for magnesium oxide first sample and second magnesium oxide sample. The important thing is that this theta value in the calculation of crystalline size by using Debye-Schreiber equation should not be in the angle. It should be in the radian. So we have to convert that, not the theta, this beta values. We got the beta values from the maximum intensity half width peaks, and that value comes from the x-axis where there is a 2 theta or theta value. So we got this as an in angle, and that angle has to be compulsory converted into the radians. So how degrees is converted into radians? We got the angle in degrees unit, and it has to be converted into radian. This is a mathematical formula which converts from degree to radians. That degree multiplied by pi values by 180, and pi is nothing but the 22 by 7, which is 3.14, close to 3.14. So by putting these values, we convert degree beta D values into beta radian for both the samples of magnesium oxide. So here we got the radian beta values for first sample and radian beta values for the second sample. So putting these values, we got in the Debye-Schreier equation, we got the answer 25.31 in nanometers. Here, the lambda value should be in the nanometer compulsory if you are determining the crystallized size in the nanometer. Otherwise, you will get the crystallized size in the Armstrong unit. So 1.54 Armstrong unit is nothing but the 0.154 nanometer. So we got the answer 25.31 and 19.13 by calculation. This research paper gives a table. So we consider only this line because we have did the calculation with the help of 200 for sample 1 and 200 for sample number 2. And D values, their D values 25.29 exactly or closely matches with our calculated D values. Since we took the average, approximate lambda values, we could take the approximate theta values. We took approximate K values. So we got the approximate D values. And that D values almost matches with the calculated values from that research paper 25.29 and 19.09. So similarly, we can calculate the A values for all from the all D values. D values we can get from the diffraction pattern, and we can find out the volumes of unit cell also. So this is a published paper, and that published paper we analyze for X-ray diffraction for magnesium oxide crystal. Few parameters we analyze. Is that clear?
Yes, sir.
Okay, last
Yes,
5
sir.
minutes. Last 5 minutes. In case of asymmetric structures like monoclinic and triclinic system, we don't use this particular mathematical calculation because calculations required very tedious calculation. So auto indexing using software, computer algorithms, the auto indexing is there, and in the most of the research paper, the auto indexing is considered. And using data, the unknown compounds is compared with the reported compounds using some standard data, JCPDS, which is called as a Joint Committee on Powder Diffraction Standard. Nowadays, it doesn't exist, but still many researchers used as a reference as a JCPDS data, which is available in the literature. Now, the JCPDS is also called as a ICDD. Its full form is a International Center for Diffraction Data. After 1978, this was exist, and this ICDD is not freely accessible. Researchers must pay the membership or subscription charges, and we can get the auto indexing of each peak with the reported data with our complex or unknown data. In case of inorganic crystal, there is a database more than 20,000 crystals, 2 lakh crystals are there, which is called as a inorganic crystal structure database that is also available in the literature. And by comparing the standard known crystals with the unknown crystal by matching, the auto indexing is possible for all 7 crystal system and 14 Bravis lattices. That facility is available. So, but for auto indexing and analyzing any X-ray diffracted data, NCL, they took near about 10 to 12,000 rupees for the analysis. So this is one of the research paper. JCPDS number is there, card number is there, and this sample of zinc oxide, this peaks matches. So auto indexing is done with this peak, this peak, this peak, and we got what kind of cubic lattice is there. That unknown sample we can easily analyze. This is I told you about the ICSD. More than almost 3 lakhs crystal structure data is available in ICSD in the crystalline sample. So ICSD card is there that matches with the unknown sample. So diffraction pattern is easily get in the fraction of second by using auto indexing. That is possible in the advanced research laboratory. Okay. This is fabrication. Lanthanum titanium oxide. They analyze with the application of lithium ion batteries, and they found that one crystal of lithium titanium oxide having proportion of lithium is 0.5, titanium is 1, stoichiometry and oxygen 2. They found that very interesting crystal structure. At different condition, they got different crystal structure, and different condition, they got different crystal structure. So one shows a monoclinic and one shows a hexagonal crystal system, where the diffraction pattern is a 003, 104, 001, such type of pattern is observed. And this phenomenon in chemistry, we call it as a polymorphism. One crystal gives two or more than crystalline form, which is called as a polymorphism. So that is a purpose to explain only this particular slides. Okay, exactly, it is a 5 o'clock. I will stop over here. Can you take a screenshot of this powder pattern of alpha polonium? Can you see this?
Yes, sir.
Yes, sir.
Yes.
Okay, take a screenshot of this.
Done, sir.
Okay, one more also. These are the powder diffraction patterns of two different systems. One is alpha polonium and one is a magnesium oxide, and both are cubic. 2 theta values I have mentioned to each peaks. You have to find out as an assignment. You are supposed to submit this assignment to Siraj sir. You have to find out what type of lattice, cubic lattice for alpha polonium, and what type of cubic lattice for magnesium oxide crystal. And what are the lattice constant A values for magnesium oxide and for alpha polonium crystal. Is it okay till Saturday?
Yes, sir.
Yes, sir.
Okay. So convert 2 theta into theta, then
Yes,
1000
sir.
into sine square theta, 1000 into sine square theta by common factor, then h square plus k square plus l square, then HKL Miller indices. From that, confirm what type of sequence is there, confirm FCC, BCC or simple cubic lattice, and then find out the A values and capital D values also you can find out. Sorry, you cannot find out because it requires a beta D values. So till A values, lattice constant, you can do the calculation and submit this as an assignment. Two assignments related to X-ray diffraction. Any questions, students?
Sir, could you repeat what point we have to find out, please?
Okay, you have to find out what type of Bravis lattice, cubic lattice is there in the alpha polonium and magnesium oxide. These are the XRD pattern. 2 theta value is already given at the peak position. Whether it is a simple body centered or face centered. And second one is what is the A values and what is the volume of unit cell.
Okay, sir. Thank you, sir.
A values and what is the volume of unit cell. Okay.
Okay, sir.
Any question? Any query?
Sir, lecture was very nicely presented by you.
Okay.
We enjoyed these 2 hours.
Okay. Thank you.
Sir,
Sir, hello.
Okay. Okay.
Sir, I have one more question.
Okay.
Actually, the calculation which are mentioned over there,
Yeah.
that is applicable for only cubic crystal system, means
Yes. Only for cubic crystal system. For
we
hexagonal, tetragonal, the formulas are different.
okay.
Planar formulas are different.
Okay, means that the diamond type simple cubic body
Yeah.
centered FCZ, that is only for the cubic crystal system. That is one of the
Yeah.
seven crystal system.
One of the
But
7 crystal system.
but for the rest of the crystal system, we can we apply that formula?
That formula cannot apply. There is another formula. I will say